Well, hello there, fellow YouTubers and beginning programmers. So, today I wanted to talk about a linked list. I wanted to demonstrate how to create a linked list in C. And before we get to that, though, I wanted to talk about what they are and what their components are, what are their basic operations, why are they necessary, and why they are important. Linked list is basically a list of things, of basically a list of data. And one characteristic about the linked list is that it can grow dynamically. So you can indefinitely grow a linked list until your program's memory is all used up. Hypothetically, you of course probably wouldn't want to do that, but their key feature is that they can grow. One thing about the linked list is that you cannot just get random access to the linked list. You have to start from the beginning, something that's called the head, and you walk through the nodes. So, and let's take a look at a better diagram where I can explain these things. But before we get to that, let's talk about why they're important. So linked lists are important because they're one of the basic structures in computer science. So the linked list can actually be used to create other more advanced data structures such as stacks and dynamic arrays and just so many different things with the linked list. And linked list is also has the features that are required by other data structures. In a linked list, you typically have data and you have a pointer to the next, but in other data structures like the trees and everything, you have a left node and a right node, but you implement the same basic concepts. They're a little bit different, but it's some of the same basic concepts. So you have data and a pointer to the next. So let's take a look at a better diagram. So here's the linked list, and don't look at the whole diagram. Let's take it one step at a time. So for a linked list, typically you have a place, you really have pointers because you're working with pointers. So the first pointer that you have to linked list is the head. And the head is always going to remain the head. Well, it may actually point to a different pointer if you insert something before the head, but let's not get into that just yet. So the pointer is really just a number. It's an address to somewhere in memory, and that memory is a heap. So you have the head, and it points to the first element in the linked list. So in that node, that's the head node. This is actually the head pointer, not the actual head. This is actually the head. So then that also has another pointer, and it points to the next item in the list. Now in this diagram, you can see where it points from the head to the node, and then from the next you can get to the next node, and from the next you can get to the next node, and finally you get eventually to a pointer that points to no, and that's a special place in memory. And sometimes you can track the tail and just keep track of the tail. So in this case, we have a tail pointer that points to the tail. This is the actual tail. This is just a tail pointer. So when you get to the end, so for example, if you wanted to insert something at the beginning, well, you can go to the head and insert it. However, if you insert at the head, you'll still have to know what comes next. So if you take the head and you immediately point it to another node that now becomes the head, you have to hold something temporary that will point to that. So typically the steps to do that are that you create a new head. So let's say, for example, that I had this head. Let's do this. Let's say that I created a new pointer and I'm going to insert it. For some reason, I want to insert it at the beginning of the list. So I insert it there. So the next thing that I want to do is maybe take this pointer, this next, and point it to what the head is pointing to. So I can set next equal to head, which is actually going to point this here. Let's see. Let's do that and do that. And so it would point it there. So now I have this, but nothing is pointing to that at this point. So I couldn't actually reach it. So immediately when I do that, when I have, it could be a temporary pointer or something, I need to immediately take this, and if I can erase this piece here, and I'll erase all of this, I take my head pointer and I can take it and point it here. And I'll avoid the arrow because it just takes more time than we need. So now my head is pointing here. So this is my new head and it points to next and next. Now, if I wanted to insert or append to the end of the list, then same thing, I would find the end. And the way I find it, I go to the head, find next. Is it null? No. Keep going, go to the next one. So it's not null. So I take the next, keep going, find it. Finally, it gets here and I find that next is null. But in order for me to point it, so now I have this, I need a pointer to this in order to get next from that and point it to a new node. So I would insert that and then make the other one null. And we'll see it in code. So don't worry too much about that detail. Just keep in mind that they're nodes. Now, one of the things about it is that the linked lists are created in memory. Let's assume that this is your memory, right? And each one of these is a node. So when you allocate memory for a node, it's going to take however many bytes based on the data in the pointer. Pointer is just pretty much fixed, whether you have 32-bit or 64-bit, it may be different, but for the most part, the pointers themselves are fixed. The data that they point to is not fixed, so this may actually be more blocks. We're just assuming it's one block, but it actually can be a block of so many bytes. So, and in memory, the thing about the linked list is that they can be in random order. So for example, you may have a list and you do some processing, you do a whole bunch of different things, and then later on you want to add something to it. So you would add a next one. So you don't necessarily know where in memory it's going to occur. It's different in an array. If you see the array here, even when you dynamically allocate an array, all the segments are in sequence. They go, in that order, and you can actually move the pointer one next and it'll get you there. You can't do that with the list. If you move to the next item, if you increment the pointer, it'll take you to the one next to it, which is not necessarily the one it's pointing to. So it can be all over the place. Actually, it could go from here to here and then maybe even jump back to here. So you just never know. But the thing about the list is that it can grow, whereas even the dynamic arrays, they can't really grow. You can reallocate them and copy all the memory over and everything, but you never know where they're going to end up. They might end up somewhere totally different. So the arrays can't really grow unless you reallocate them. And arrays themselves can, if you have a dynamically allocated array, then it can grow. But just a regular array, you're fixed. So if you need more items, or if you don't know how many items you're reading, for example, if you're reading from a file, and that file may have sometimes 1,000 items, sometimes 5,000, you don't necessarily know how many to allocate. You may be wasting a lot of memory. Let's say, for example, if you allocate, 10 times what you need. So you may want to do it in increments. So that's where a linked list really shines. And the thing about the linked list, it also helps you create other data structures that may need to navigate. So this is what they call a linked list, but it's also known as a singly linked list because you only have a pointer to the next. You can have a doubly linked list where it actually points backwards, so that way you can point to the previous item. They're a little more complicated, so we won't get into that. Just keep that in mind that you can have, in this case, next just points here and so on. And roughly what a type that this may not be 100% syntactically correct, but this is essentially what you have in C. You have a type diff, a node. Well, actually, you need struct there. It's a struct, and structs, as you can know, you can have more complex objects in C. In this case, we have an integer for the data, but the data could be anything. Actually, you could have more data elements in that node, but sometimes you just have maybe pointing to another struct type. Maybe you have another struct type that holds your data, or you can get into dynamically having or maybe having a generic list, which is a little more complicated in C. It's easier in other languages such as Java and C# and so on, because you have you have generics where you can store any type of data you tell it. But in C, it's a little more complicated, but it still can be done with void pointers and all that, which is a little bit more advanced. So we won't really get into that. But this is the essential concepts of a linked list. It's just the idea that you have a list, and you have to always know your starting point, and you have to walk it. You have to go in order. I can't jump, for example, from the list and find out the pointer unless I save my pointer somewhere that, like in this case, if I'm saving a pointer to the tail, then I can always get to the tail. But even if I can get to the tail, I might not be able to go walk myself backwards because I only have next, so it can only go to null. Null is a special place in memory. So when you walk the list, you have to start from the head, walk, and you'll see a lot of those algorithms when you're adding and removing items and so on to the list. Now, it gets a little complicated when you want to remove, for example, an item. Let's say we wanted to remove this item from the list. So far we know that we start with the head and we start adding elements. We can insert at the beginning and we can append at the end. And appending at the end, of course, you just take this next, create a new one, and the next one will point to null. But what if you want to add somewhere in the middle? Well, it gets a little complicated because you have to have a pointer to the previous one and you have a pointer to the next one. So what you have to do is kind of create a new node, in this case something like this. You take this, that's not what I meant to do, I meant to select it. So you take this node, like let's say you create a new node, not this node necessarily, but you create a new node, and let's say we put it right in here and we want it in between these two. So what I would have to do, I need a pointer to this one, and I'm going to disconnect it and point it up here. So in order for me to do that, I have to make sure that I hold another pointer that points to this one. So what I want to do is I want to hold a temporary something equal to this. So I take another node pointer, and I can call it temp or whatever I want. So for example, I call it temp, a temporary pointer, and I take and I point it to this, right? So by me setting next, my temp equal to next, it automatically points here. Then I take next and I point it to my new pointers, which is going to be here. And let's do this in a different color. So then I take that and I point this here. Now this is no longer connected once I point it because it can only point to one location. Then what I do is I take this next here, make it equal to my temp, which is going to point it here. So now my linked list, the path that it follows, it goes from here to here to here to here, here, and then from here it just goes on to that. So it gets a little tricky, but it's really not that complicated. You may have to play with the linked list a few times in order for you to get it, but let's take a look and let's go ahead and start coding and see what we can accomplish with that. So what I have here is your typical definition of a struct. And I chose to use an alias, that way I can do node and I don't have to use type dev struct every time that I want to declare a node. So in this case, I just have a type dev struct. I have my data, which is integer type, and I just called it data. And then my struct node def, which I call next, and let's make it uppercase to be consistent. So right now we have something just very simple. We have a node, we have a pointer to the head, and we're dynamically allocating memory of the size node. This will make sure that we get the right amount of blocks, so it's going to have enough memory for an integer and enough of that. And let me double check myself because I think I may have the size of wrong. So let's go back here. So we're allocating the head. So if we wanted to append to our linked list, very simply we can say, now keep in mind here, one of the things that we're not doing is we're not setting this to null. So one of the first things that we want to do is we want to set the node to some data, but we want to also point the next to null. That's the first thing we want to do. So we can say equals null. And since C has defined null, which is defined in several libraries, I include stdio and stdlib. I believe it's in, I know definitely it's included in here in stdlib. So that's the first thing we want to do is create the size of the node. So we dynamically allocate it. But since we know we're going to do this repeatedly whenever we want to create that node, one of the things that we want to do is maybe create a function that just gives us the node when we allocate one. And we say node and we say create. Sometimes people say create link or create node. So, and we pass it the data. And we can take this code here. Of course, this is not going to be the head. This is not going to be called something, just a node. And since we're going to do it every time, we allocate the node and we have to change the names. So node, 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 and we return the node. head. Oh, I don't know why I'm not liking it, so let's save it. So we have the node, we're allocating it. So this is to create our link. So instead of doing all of this, we can now take and we say create link, and we have a node pointer. And the first thing we want to do is point the head to that link equals, and we say create link. And let's do a little more C-like. So we say create link. And we pass in the data that we have. So in this case, let's say, for example, 10. And this should still continue to work. So let's go ahead and take this and compile it from the command line. And see our compile command. So let's call it exe since we're in Windows. And so let's execute it. And we see, oh, this didn't execute because we should have 10. So why did we get a 1? Oh, because we set it to 1. We didn't save it to the correct data, so we need to make sure that we save it to the data. Otherwise, it's going to be a hard-coded 1. And let's recompile it. And let's go ahead and run it. And now we get 10. So we could just create links. And so we can continue just adding links. So we could say head next. Or not, it's uppercase next equals, and we can call create link again, and this time we create 20, and let's say that we add 30. But right now our list is not going to display the entire list. So if we wanted to display the list, we can take, and one of the things is, let's go ahead and create a function, and we say make it void and print the entire list. So print, and we can pass it the list. And list, sometimes it's used interchangeably. I'm calling it list, but I'm really needing to pass the head in there. So it's up to you how you want to do that. And one of the things to walk the list, we can say, so the first thing we want to do is get the head. So let's say, sometimes you want to save a pointer to the head. So we have the list here. So we could just say, wow. And sometimes it's just better practice to have a temporary node. So let's say, for example, that we have a node. And we call it maybe a temp variable or something. Or current equals list. And we can say while current not equal to null. And then we can proceed to do our printf, and we just take it and copy it. And we copy this, and of course one of the things we have to do, of course, is current, not that. And in order to walk our list, remember when we said that we have to walk the list in order. So one of the things we have to do is take and walk our list in order. So we have to say current equals current next. And what this does, it essentially walks the list to the next node, like we saw in our earlier diagram. Let me pull it up. In our earlier diagram here, what we're doing is we're here, we print it, and we look at next and go to the next one. And so it's just in a loop. We're able to put that in a loop. So that should print our next until it gets to null. And that's why it's so important that whenever you create a node that you initialize it to null. That way we know that we always start off with the know that their next is null. So every time we're creating a link here, we're creating a node where we're passing in the data, we copy the data, and we initialize it to null. So that way it always becomes the tail. So we're creating a link there. So now when we call our function to print, instead of saying printf, we could say print, and we pass it just the head. And it should print our list and see if we did everything correctly. So let's go ahead and take a look at it. Let's go ahead and recompile it. No errors. And oh, well, one of the things we didn't do is we need to either provide a comma or something. Let's just make it simple like that, comma. So let's go ahead and recompile it. And all our elements are separated by commas. As you can see, 10, 30. But one of the things about it is that we have 10, 30 and we don't have 10, 20, 30. So something went wrong. And the reason for that is because here we said head next and head next equals that. And then we overwrote the next. So you got to be careful with that. So in this case, we would have to say head next, next. And you can see the problem that if we keep doing this next, 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 it's going to create problems for us. So let's go ahead and recompile that. Let's clear this. So let's go ahead and take that and recompile it. And now I should and now it prints that. Of course, you don't want to do this. So let's create an append method, or let's create an append method. So let's say that we wanted to append to the list. And we always need the head, so let's go ahead and we have the list there, and we can take our so since we want to append to the end, what we want to do in this case is sometimes it's easier to use brute force with these linked lists. So one of the things that you want to do, the first thing you want to do is say if, for example, and this is where it gets tricky because that's where you may need a pointer to pointer, because you may actually need to point that to the head. So for example, you may actually need a pointer to a pointer in order to append. That way, when you have the list, you can actually append. But let's assume that we already have a head. And we know we have a head. So we're appending to the head. And so what we want to do in this case, we don't want to walk all the way to the end of the list. We want to walk one prior. So we want to go one next while it's not null. And we just walk and keep walking. That way we don't walk all the way to the end of the list. And then here we just say, now when this is going to go all the way to the end where the last, it's going to walk to the tail, next is going to be equal to null, so it jumps out. So now we can say current next equals, and of course we didn't have our data. So we need to have our data. We need to have our int. And so when we append, we can just say create link. And now we can append. So now instead of doing this, we can actually append to the list. So let's see if that works. So let's go ahead and append instead of doing all this. And so we're appending to the list now. So let's go ahead and recompile. Oh, we get an error, append. Okay, too few arguments because we need to pass it the head. Pass it the head. So, and, oh, not there. That's a mistake on my part. So we need to pass it the head every time. And so we're appending and we're passing it to head. So let's see if that works. And let's try to recompile it again. Compile this time, let's clear it so we can have more real estate. So let's go ahead and run it. And you can see that it worked. So that's one of the things that you want to do. That's inserting at the end of the list. So what if you wanted to insert at the beginning of the list? So let's create another function, and this time it's going to be a little bit different, and we're always going to assume that we have the head. So now what we want to do in this case, this is kind of different. What we want to do is take the list and we're going to create a temporary pointer, right? So what we want to do is, since we want to insert, and we're assuming that we have something, that we actually have a head, not that we have a null head, just to make things simpler. So the first thing we want to do is we want to say node, we'll say old head or something, or previous head equal list. So now this becomes a problem because, okay, so let's say we're calling it insert. because this time what we want to do is, since we're inserting, and we're actually inserting just at the beginning, not just anywhere. So what we want to do is return a pointer to the new head. So now the previous head equals the list, right? And so we take our pointer from the previous head equals the list. So we want to insert our data. Well, of course, we want to create a link, and our previous head next is not going to be create link. Actually, our head is going to be equal to the link. So now what we want to do is take we want to create a link. So let's just say node. Let's just call it temp for lack of better, equals create link. Now the temp next is going to be pointed to the list, right? So now temp next equals the point to the list, and what we want to do is point the head, but we don't have a pointer to a pointer. One way to do it is to have a pointer to a pointer, but we're not going to do that. So what we're going to do instead of doing that, we're going to return temp, which is the new head. And what we can do here is take our head and insert, and of course we have the old head here, and let's insert something lower like 5, and let's print it and see if this works. Go ahead and recompile it, and we should have 5 at the beginning, and we do. So we have our insert and we have our append. Now there may be times when you want to insert in the middle of the list. We won't get into that, but typically it's something that if you want to maybe keep things sorted and you want to add in sort order, then you have to figure out, you have to do a combination of walking the list and finding the place to insert. And there's some special cases, because if your item, say for example you have a sorted list, and let's say that, let's just create the function. So let's say that you want to keep it in order. So insert order, right? So I'm not even going to create the parameters. So let's just say that I did that and return null for now. So let's say that you want to insert and you have a list where you have 1 and 5 and 10. Well, there's different case scenarios, because if you want to insert, say for example 0, and you wanted to keep it in order, you're going to insert it to head. So this is when a special case when you insert head. If you have, for example, the number 11, then it's going to go at the end. So there's a different way to insert at the end, because now you're inserting at the tail, right? And so then there may be there's another case where maybe it's a 3 or a 7, and you're going to insert somewhere in between. The 3 would be somewhere in between 1 and 5, and the 7. But I'll leave that as homework for you. See if you can handle that, and leave your comments and point to your solutions below in the comments if you do solve this. So we're not going to solve this right now, but I'll leave that up to you, and I'm going to create a link and post it here. So there's another case where you may want to delete, and it's very similar. If you want to delete something, you just have to point things in the right place. But essentially, that is your linked list. You saw how to print it, you saw how to append, and you saw how to insert. There's more things that you can do with the list, such as one of those being keeping it ordered, and also having generic data, because you wouldn't necessarily want to create all of this every time, all these algorithms for every data type, float and string and so on. So you may want to have something more generic, like a void pointer or something like that. It's a little bit challenging in C, but it can be done. So just keep that in mind. There it is. Thanks for watching. If you like it, give it a thumbs up. If you have any questions, leave it in the comments. And like I said, I'll post the link to the source code below. So thanks for watching. So hey guys, you're still here. One thing that I left out is that you always have to clean up memory whenever you're working with dynamic memory allocation. I left that part out, and it's very important because you can get some really weird errors in your code. So one of the things about this is that you have to free the memory. So in order to free the memory, since you're working with a linked list, you're going to have to work it somehow in some kind of order. So one thing you want to do is let's just call it clean, and we pass it the, let's say we pass it the list, and you're gonna have to walk the list. So let's take a look at here where we walk the list, and you gotta make sure that when you're cleaning up that so we're walking the list here, and we want to clean it. And one thing would be to say current equals, current equals whatever, but we can't really do that. So what we want to do is we want to hold something. So we want to navigate, not necessarily navigate to next. So let's create a node pointer. Temp equals current, and we have a pointer to the current, and then a pointer to the next, and we delete temp, and that should delete the list. And so there we have the list where we're deleting everything, freeing everything up. Now that may cause a problem because even after you clean and then you try to access head here was pointing somewhere. That's not, you didn't necessarily repoint this to null, so you have to point that to null. So one of the things you want to do is, since you, let's see, we're having a pointer to the current, and then we walk it, and then we delete temp. So before we delete a temp, we got to point it to the next item in the list. And one of the things here is current next not equal null. So that might not get us there. What we actually want is current not equal to null, because we want to walk it all the way to the end of the list and delete everything. So once current is null, then we don't have to delete that. So that should clean it up, and that's all you have to do to clean it up. So let's go ahead and probably better name would be clean up. So we say clean up. Pass it to head, and it should clean up. But keep in mind that, like I said, at that point you haven't cleaned up the head because the head's still pointing somewhere invalid in memory, so you get an error if you try to do that. So, and actually we want to clean up after we print, after we're done. And then of course we want to also point the head to null. But since we deleted the head, we don't need to free it up anymore. So actually it shouldn't be delete, it should be free. And that should do it. Let's run and see if we get any errors. Actually, okay, head equal, oh, I always forget C++ has no lowercase like that, but, and did we do that with these guys? Okay, so we shouldn't be pointing to anything anymore. So let's go ahead and build it, and that should clean everything up. Of course, you won't see anything. You won't see anything there. It just clean up. So there you are. That's how you clean it up. And like I said, I'll post the link to the code in the description of this video. Thanks again.